Hi dear students, hope you all are fine and well. Today we are going to learn about an important topic in econometrics. Actually, this lecture is a part of the econometrics syllabus of the postgraduate program of economics under Kannur University. Therefore, the scope of the lecture is strictly confined to the syllabus. From the earlier lectures, we have seen that how do we frame an econometric model with the usual classical linear regression model assumptions? Our present discussions are going around the violations of these assumptions. We already discussed regarding the sources, detection, and remedial measures of the problem of multicollinearity and heteroscedasticity. I hope that all of you were gone through the lecture notes of the earlier classes. If not, I request you to go through it once again. Today, our discussion will be on the phenomena of autocorrelation, its definition, sources, how do we detect it, and what are the remedial measures should be taken if our data shows autocorrelation. I have divided the lecture into 4 parts. In the first part, we focus on the definition of autocorrelation, what are the possible pattern of autocorrelation, and what are the important reasons for or sources of autocorrelation. In the second part, we will focus on the estimation in the presence of autocorrelation. What were the consequences of using ordinary least square method if there is autocorrelation, and what is the best linear unbiased estimation in the presence of autocorrelation. In the third part, our discussion will be focused on the various methods to detect autocorrelation. In this part, we discuss the graphical methods to detect autocorrelation. Also, we discuss various tests to detect autocorrelation. The Run's test, the Durbin-Watson D test, and the Bruce-Godfrey test are the major tests that would be discussed here. In the fourth part, we should concentrate on the various remedial measures that should be taken if there is autocorrelation. You will get all the 4 parts, all the 4 lectures in 4 separate videos. Kindly go through the lectures. The major reference text that I used for the present lecture is the Basic Econometrics written by Damodar Gujarati. I also referred the Introductory Econometrics written by Jeffrey Woolrich wherever necessary. Autocorrelation simply means the correlation among a given set of data and a lagged version of itself over some successive time intervals. The data in question is usually the time series data. There is only one difference between a simple correlation and autocorrelation. In simple correlation, we examine whether the 2 different series of data are correlated or not. But in autocorrelation, we use the same time series twice, once in its original form and once lagged by 1 or more time periods. The word auto in the autocorrelation is from the Greek word for self, and hence autocorrelation means data that is correlated with itself. Therefore, the term autocorrelation can be defined as correlation between members of a series of observations ordered in time or space. If the observations are ordered in time, the data will be a time series, and if the observations are ordered in space, the data will be a cross-section. In the context of classical linear regression model, we assume that our data does not exhibit autocorrelation among the disturbances or error terms. Symbolically, thus the no autocorrelation assumption can be represented as expectation ui uj is equal to 0. That is, the correlation among ui and uj is equal to 0, where I is not equal to j. That is, the disturbance term relating to any observation is not influenced by the disturbance term relating to any other observation. When there is violation of this rule is found, then we have a problem, and that problem is known as autocorrelation. For example, if we are dealing with the quarterly time series data of the GDP of a particular country, we generally assume that a rise or fall in the GDP of this quarter due to some reason may not carry over to the next quarter. Similarly, the output of a factory is lower this quarter due to maybe a strike among the employees. We do not expect that this disruption in output is carried over to the next quarter. If we found a momentum is inbuilt in the movement of GDP figures among successive quarters, or a momentum can be found in the output of the factory among the successive quarters, or if a momentum is found among the movement of the stock prices, we have the problem of autocorrelation. Cross-section data also sometimes exhibit similar trends. For example, if we are dealing with the data involving the regression of family consumption expenditure on family income, we found signs of demonstration effect. That is, a rise in consumption expenditure of one family may very well prompt another family to increase its consumption expenditure. Here also we have a problem of autocorrelation. Although it is now a common practice to treat the terms autocorrelation and serial correlation synonymously, some authors try to distinguish the two terms. For example, Gerard Tintner, an Austrian-born American econometrician, defines autocorrelation as lag correlation of a given series with itself, lagged by a number of time units, whereas he uses the term serial correlation to lag correlation between two different time series. Thus, correlation between two time series such as U1, U2, etc. to U10 and U2, U3, etc. to U11, that is, where the second series is lagged former series by one time period, this is autocorrelation. Whereas correlation between time series such as U1, U2, etc. to U10 and V2, V3, etc. to V11, where U and V are two different time series and V series is lagged by one time period. This is the case of serial correlation. By following the convention, hereinafter we are also used both terms as simultaneously or interchangeably. Let's see 5 different possible patterns of autocorrelation among the 5 diagrams attached here. Among these 5, first 4, that is figure A to D, shows that there is an obvious pattern among the stochastic terms. Figure A shows a cyclical pattern among the disturbances. Figure B shows an upward linear trend, and figure C suggests a downward linear trend in the disturbances. Whereas in figure D, both linear and quadratic trend terms are present in the disturbances. Only figure E indicates no systematic pattern, supporting the no autocorrelation assumption of the classical linear regression model. If our data exhibit any of the first 4 patterns in its disturbances, we have a problem of autocorrelation. Why does autocorrelation occur in a given set of data? Or what are the sources of the problem of autocorrelation? There are several reasons can be cited. Some of them can be discussed here. First important reason is that the state of inertia or sluggishness or the tendency to maintain the status quo. It is an important feature of most economic time series. This is more particular in time series such as GNP, price indices, production, employment and unemployment characterized by cycles, or we call it as business cycles. Starting at the bottom of the recession, when economic recovery starts, most of the series starts moving upward. In this upswing, The value of a series at one point in time is greater than its previous value. Thus, there is a momentum built into them, and it continues until something happens to slow them down. For example, increasing interest rate or taxes or both. Therefore, in regressions involving time series data, successive observations are likely to be interdependent, that is, auto-correlated. Another reason that can be cited as specification bias due to exclusion of variables. While doing an empirical investigation, the researcher often starts with a reasonable regression model that may not be the most perfect one. It is only a reasonable approximation of reality. After the regression analysis, the researcher does a thorough examination to find out whether the results are in accordance with the a priori expectations and theoretical conclusion. If the results are not in accordance with the a priori expectations, the surgery is begun. For example, the researcher may plot the estimated residuals, that is U hat I, obtained from the fitted regression and may observe patterns. Recall that U hat I is the residuals and a hat or cap on U indicate that they are the estimators which are used as proxies for UI. The results may suggest that some variables that were originally members but were not included in the model for a variety of reasons. This is the case of excluded variable specification bias. If we include such variables, we can remove the correlation pattern observed among the residuals. Generally, we express the quantity demanded for a commodity is a multivariate function of the price of the commodity, income of the consumer, and price of the related or substitute goods. In the same way, suppose we have the following demand model. Yt is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus beta 4 x4t plus ut, where Yt is the quantity of beef demanded and it is expressed as the function of x2. x2 is the price of beef, x3 is the consumer income, x4 is the price of chicken, which is considered as the substitute goods for the beef, and the subscript t denote that the data is ordered in time, that is time series data. Now, however, for some reason we run the following regression instead of regression equation cited as above, that is Yt is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus vt. You see the difference between the two equations. In the first equation, we have an additional variable in the form of the price of substitute goods, and in the second equation, that variable is not there, and therefore the error terms are of both variables, both equations are different. So that means in the second equation, we did not take account of the influence of the price of chicken. Now, if equation 1 is the correct model or the true relation, running equation 2 is also equivalent to equation 1 if we let the error term Vt is equal to beta 4 x4t plus ut. But the error term Vt will reflect a systematic pattern, that's creating autocorrelation. This type of autocorrelation is often considered as false autocorrelation, given that the inclusion of the additional variable to equation 2 to make it equal to equation 1, the problem of autocorrelation disappears. Next important reason for the problem of autocorrelation is the specification bias due to the incorrect functional form of the model. Suppose the true or correct model in a cost output study is given as marginal cost of I is equal to beta 1 plus beta 2 into output of I plus beta 3 into output squared of I plus ui. That is, marginal cost of a firm is a quadratic function of its own output. The subscript I denotes the ith form, meaning the data in question is a cross-section data. But unknowingly, we fit the following model. Marginal cost of I is equal to alpha 1 plus alpha 2 output I plus Vi. That is, the marginal cost as a linear function of the output. Now let us look at the diagram. Here, the marginal cost curve corresponding to the true model is shown in figure along with the incorrect linear cost curve. The problem with this kind of specification is that between point A and B, the linear marginal cost curve will consistently overestimate the true marginal cost, whereas beyond these points, it will consistently underestimate the true marginal cost. This result is to be expected because the disturbance term Vi in the linear model is in fact equal to output squared plus ui, and hence Vi include the systematic effect of the output squared term on marginal cost. In this case, the disturbance term Vi will reflect autocorrelation because of the use of an incorrect functional form. Cobweb phenomena is another reason for autocorrelation. The supply of many agricultural commodities generally reflects the so-called cobweb phenomena. That is, supply reacts to a change in price with a lag of one time period. We cannot immediately increase the supply. There is a gestation period involved. If the price of onion increases, the farmers may invest more on the cultivation of onion. Thus, at the beginning of this year or this season planting of crops, farmers are influenced by the price prevailed last year, so that their supply function becomes supply of this year or this period is equal to beta 1 plus beta 2 into price prevailed during the last season plus ut, an error term. Suppose at the end of period t, price, that is price of this year, turns out to be lower than price of last year. Therefore, in period t plus 1, that is next season, the farmers may decide to produce less than what they did in period t. Obviously, in this situation, the disturbances are not expected to be random, because if the farmers overproduce in year t, they are likely to reduce their production in t plus 1 and so on, leading to a cobweb pattern. Lagged responses to decision variables are very common in time series data. Therefore, the time lag itself becomes a source of autocorrelation. For example, in a time series regression of consumer expenditure on income, it is customary to view that the consumer consumption expenditure in the current period depends, among other things, on the consumption expenditure of the previous period. That is, consumption of this period is equal to beta 1 plus beta 2 into income of this period plus beta 3 into consumption of last period plus error term. This model is an example of autoregression or AR model, because one of the explanatory variable is the lagged value of dependent variable. You can see here that consumption is the dependent variable and its lagged value become the independent or explanatory variable. Why do we use such models? The rationale for it comes from the fact that the consumers do not change their consumption habits due to psychological, technological, institutional reasons. You can recall the dynamic models on consumer behavior studied as part of your microeconomic theory, such as Nerlow model and Hothacker and Taylor model, where the past purchases either constitute a stock of durable goods or a habit of consuming non-durable goods. Therefore, past purchases on durable good reduces the demand for durable goods during the current period, because we already had a stock of it. and past purchases of non-durable goods may increase the demand for that good because we already made a habit of using that. Now return to our example. If we neglect the lagged term, that is consumption of the previous period, the resulting error term will reflect a systematic pattern due to the influence of lagged consumption on current consumption. Therefore, autocorrelation is inevitable. While doing the empirical analysis, we often manipulate the raw data. Those kind of manipulation becomes a reason for the problem of autocorrelation. For example, in a time series regression involving average monthly production in a quarter, such data are usually derived from the monthly data by simple arithmetic average, that is, simply adding 3 monthly observations and dividing the sum by 3. This averaging introduces a kind of smoothness into the data by dampening the fluctuations in the monthly data. Therefore, the graph plotting the quarterly data looks much smoother than the monthly data, and this smoothness may itself lead to a systematic pattern in the disturbances, thereby introducing autocorrelation. Another kind of manipulation is interpolation or extrapolation of data. These are two important ways to estimate or construct hypothetical values for a variable from a given set of observations. Interpolation allows us to estimate within a dataset. It is the process of estimating unknown values that fall between known values. In simple words, for example, if we estimate the mid values of two known points, the midpoint is an interpolated value. Take an example. The population census in India is conducted in every 10 years, the last being taken in 2011, and the one before that was in 2001, and the next we will do it in 2021. Now, if there is a need to obtain data for some year within the inter-census period of 2001 to 2011, the common practice is to interpolate on the basis of some ad hoc assumptions. In extrapolation, we go even further. It is kind of extension or expansion of our experience and expertise in one area to another area of that we do not know or that we have not experienced yet. It is more hypothetical than interpolation. In the previous example, if we want to estimate projections on the population of a country for the coming decades, for example, by 2051, we use extrapolation. In short, interpolation is guessing data points that fall within the range of data we already have. Extrapolation is guessing data points from beyond the range of our dataset. Both are data massaging techniques, and it might impose a systematic pattern that may not exist in the original data. Another source of autocorrelation is the data transformation. This can be explained with an example. Consider the following model: yt is equal to beta 1 plus beta 2 xt plus ut, where say y is consumption expenditure and x is income. We assume that the equation holds true at every time period. If it is true in this time period, it is also true in the previous time period, t minus 1. So we can write the equation as yt minus 1 is equal to beta 1 plus beta 2 x t minus 1 plus ut minus 1. We use three lagged values here: lagged values of the income, lagged values of the consumption, and lagged values of the error term. And all these are lagged by one time period. Now if we subtract equation 8 from equation 7, we obtain delta yt is equal to beta 2 into delta xt plus delta ut, where we use delta known as the first difference operator. It tells us to take successive differences of the variables in question. For empirical analysis, we use the above equation as delta yt is equal to beta 2 delta xt plus vt, where vt is the difference in error term during two successive time periods. Thus, the equation is presented here is in the first difference form. These models are also known as dynamic regression models, that is, models involving lagged explanatory variables. Now, if the error term in the original model yt is equal to beta 1 plus beta 2 xt plus ut satisfies the standard OLS assumptions, particularly the assumption of no autocorrelation, it can be shown that the error term Vt in equation delta Yt is equal to beta 2 delta xt plus Vt. In this equation, the error term Vt is autocorrelated because it includes the influence of the error term during the previous period. Therefore, sometimes autocorrelation may be induced as a result of transforming the original model. Now, while dealing with the time series data, we usually confront with the phenomena of non-stationarity. At the outset, therefore, we may have to find out if a given time series is stationary or not. A time series is stationary if its characteristics, example, mean, variance and covariance, are time invariant, that is, they do not change over time. A time series regression model such as yt is equal to beta 1 plus beta 2 xt plus ut. It is quite possible that both y and x are non-stationary and therefore the error term ut is also non-stationary. In that case, the error term will exhibit autocorrelation. Therefore, non-stationarity of the data becomes another reason for the problem of autocorrelation. It should be noted also that autocorrelation can be positive as given in figure A, or it can be negative as given in figure B. Although most economic time series generally exhibit positive autocorrelation because most of them either move upward or downward over extended time periods. Positive autocorrelation occurs when an error of a given sign tends to be followed by an error of the same sign. That is, positive errors are usually followed by positive errors and negative errors are usually followed by negative errors. Negative autocorrelation occurs when an error of a given sign tends to be followed by an error of the opposite sign. For instance, positive errors are usually followed by negative errors. Negative errors are usually followed by positive errors. Negative autocorrelation is shown in figure B. Negative autocorrelation is less common as compared to positive autocorrelation. The first part of our lecture is over. As I mentioned earlier, the other three sections of this topic is given in 3 separate PowerPoint videos. Please make sure that you are well prepared before moving into other topics. If you have any doubt or queries about the topics covered in this lecture, please bring it to my attention. Thank you once again for your patient listening.